This Physcast looks at how to find the direction of a magnetic force on a moving charge. Pause the video and read through the problem carefully. Let's begin our solution with an interpret step, which in this case is quite straightforward. We're trying to find the direction of a magnetic force on a moving charge. In our develop step, we might draw some diagrams. In fact, importantly here, we're looking for directions. We might like to think about how we can think of the coordinates in this particular problem. One way might be to draw a set of coordinates as you might normally. That might be my x direction, that might be my y direction. But importantly, with magnetic forces, they're intrinsically a 3D kind of problem. So I'm almost always going to have to consider my coordinates in 3 dimensions. So one thing I could do here is I could add my z-axis, which will either point either into the page or out of the page. In this case, and I'll remind myself that these are positive x and positive y axes that I've indicated here with the arrows. In this case, my positive z-axis will actually point out of the page. And that's what that dot in a circle is trying to indicate. And one way to remind yourself of that direction is actually using a right hand rule already, where if the fingers of your right hand curl around from the x-axis around to the y-axis, the thumb of your right hand will point in the direction of the positive z-axis. So if my fingers on my right hand go from pointing horizontally to pointing vertically, my thumb must be pointing out of the page. Sometimes people prefer to draw a kind of a 2-dimensional version of a 3-dimensional set of coordinates, where in this case this arrow here, it's something pointing away from you, pointing kind of into the page as it were, and here I might call this the x-axis, this the y-axis, and this will become the z-axis, again all in positive directions, and I could confirm that using my right hand rule. Now in this particular problem I have a positive charge q that's moving towards the positive y direction with some speed v. And in addition to that, I have a magnetic field that's pointing in the positive x direction. So here I might draw my nice uniform magnetic field. Now, how do I know about the relationship between these various quantities and the magnetic force? Well, I've got a nice equation that helps me link the force on a moving charge, and importantly, as you'll see, if the charge is not moving, or if the charge is moving in perhaps not quite the right direction, this force might not exist at all. But it's going to be equal to the size of the charge q, and then it's going to be the cross product of the velocity and the magnetic field. Because this equation contains directional information, because the answer that it gives me, this force, is a vector. In some cases, all I really care about is the magnitude of that force, and the magnitude of a cross product will be q times v times b times the sine of the angle between the v and the b vectors. In this particular problem I'm not concerned with magnitudes, but if I were, I could see straight away that this force will have its largest value when sine theta has its largest value, that is when v and b, those two vectors, are at right angles to each other. So let's move on to the evaluate step of my solution, where now I need to think about the motion of the charge and the magnetic field in terms of vectors. So I might write my velocity of the charge here as the speed v multiplied by a vector in the direction. In this case it's moving in the plus y direction, so we'll call that j hat, where the hat is indicating a vector of unit length, and j hat is by convention a vector of unit length in the y direction. And I could similarly say, well, I'll write down the magnetic field B as some magnitude that I will just call B. We're not particularly interested in magnitudes at the moment, but it's going to point in the x direction, so I'll multiply that by a unit vector in the x direction, that is the I hat vector. And now my force on the charge, which will be Q times V, which is going to be V j hat, that's the vector I have, crossed with B, which will be capital B I hat. And this V and this B, they're just magnitude, so they can all come out the front, if you like, of that cross product. And what I really have here is j hat cross I hat, and this vector, whatever it is, j hat cross I hat, that's telling me the directional information of this force vector. And so we need to think about what, this will actually give me a unit vector, but I want to know what direction it's going to be in. So what do I know about cross products? Here's something that you may know, and that is that if I do I hat cross j hat, I actually get the unit vector k hat, which is the unit vector in the positive z direction. And that if I do j hat cross k hat, I actually get I hat. And if I do k hat cross I hat, I get j hat. There's this nice cyclic relationship between these unit vectors. And one way you might think about that is I could actually kind of write them down in a circle like this. And if I go around that circle in this clockwise direction, then anytime I do a cross product of any two of these in that direction, I get the third one in a positive sense. So it shows if I did k hat here crossed with I hat, I'm going around the circle that direction, I'll just get j hat. And then I need to remember that if I change the order of my cross product, if I instead went j hat cross I hat, then I get the negative. I get negative k hat. In other words, I'm going to go around this little cyclic thing here in the wrong direction. If I go from j around to I, I've gone in the opposite direction. I'm going to get k hat, but I'm going to get a negative sign. And so similarly, I can show the rest. K hat cross j hat is minus I hat. There is one other thing that you might be familiar with, and that is a cross product using a determinant, if you know some matrix algebra. And that is if I was to take the cross product, for example, of these two vectors, v cross b, I can calculate that using a 3x3 determinant, where the first row is these I, j, and k unit vectors. The second row will be the x, y, and z components of my first vector, and the third row is the x, y, and z components of my second vector. And if you're not sure how to calculate a determinant, I don't have time to show you just here, but some of these entries will become a little bit easier. You should be able to see that, for example, for the speed in this particular problem, I know that it's only pointing in the j hat direction, so I'll have zeros there, a v there. And similarly for the magnetic field in this problem, it only points in the I hat direction, so I'll have a b there and zeros elsewhere. And again, if you know how to do a determinant, the only thing that comes out of this one, in fact, will be minus k hat and then v times b, which is exactly what I get if I use my rules, my cyclic rules here. J cross I gives me minus k, so this thing comes out to be minus k hat, that's the vector, times qvb. So minus k hat, this is telling me that the force points in the negative z direction. And we can just, for our assess step, see what happens if we try to apply a right-hand rule. So rather than doing our vector algebra here, what if we apply a right-hand rule to this problem? And the right-hand rule that I'm going to apply is the so-called slap rule, because it basically uses your right hand with an open palm. So with that particular rule, what you do is you put your thumb of your right hand in the direction of the motion of a positive charge. So if I go up to this diagram here, I'll be putting my thumb in this direction. So there's my right hand thumb just there, pointing in the direction that this positive charge is moving. And then I put the fingers of my right hand in the direction the magnetic field is pointing. So my fingers of my right hand would come out in this direction like this. And then if you think of that as your right hand, and you try this yourself whilst you're looking at this video, place your right hand thumb pointing upwards, place your right hand fingers pointing off to the right hand side of the page there, and you'll see that the palm of your right hand will be pointing into the screen. The force will be pushing into the screen. And as we've said, the z-axis here points out of the page, so that means the force must be into the page. So our right hand rule and our vector cross product algebra here are giving us the same answer. The force on this charge is in the negative z direction into the page as we've drawn it.